Woohoo! It's Friday, and it's time to do determinants and inverses of 2 by 2 matrices. I sound like what? Should I be a radio announcer? Yes, yes. Uh huh. Uh huh. Who played her? Is it Sally Field that played her? Okay. All right. So you guys, when you see Sally Field, you think of brothers and sisters. When I think Sally Field, I think Gidget and the Flying Nun, because that's who she played when she was very young. Do they have those on Nick at Night or TV Land or something? Yeah. Gidget was really good. Sally Fields was a little surfing chick. It was good. Okay, so some definitions. A square matrix. I wonder if I should try to type these. Maybe. A square matrix. Come on. Is a matrix where the rows and columns, columns, are the same size. Okay, so we'll need square matrices to do these determinants and inverses. Okay, the multiplicative identity I'm sorry, do I want a multiplicative identity? Yes, multiplicative identity is a square matrix with ones on a particular diagonal and zeros elsewhere. Alright, so what does that mean? So I'll give you an example of some square matrices. I'm sorry, multiplicative identity matrices. So a 2 by 2 multiplicative identity would be 1, 0, 0, 1. The ones have to be on the diagonal from the upper left to the lower right. So a 3 by 3 multiplicative identity would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. A 4 by 4 would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Get the pattern? Okay. And why are those important? Because pull the page down. A matrix multiplied by its, now a new word, inverse, and that's going to be very important now, is the multiplicative identity. In other words, so inverse, this word inverse, it's going to be important. So if I have some matrix A and I multiply that by its inverse and I abbreviate the inverse with, I'll write the matrix A down again and I'll put a little -1, which means reciprocal, which means inverse also. So some matrix times its inverse will equal an identity matrix. So if they're and they have to be square matrices in order to do this. If it's 2 by 2, it'll give me the 2 by 2 identity. If they're 3 by 3s, it'll give me a 3 by 3 identity. Let me show you what I mean. So we'll let matrix A be -2, -5, -3, -8. And its inverse is -8, 5, 3, -2. So let's see what happens when we multiply these two matrices. I get -2 times -8, that's 16, plus -5 times 3, -15. First row, second column, I get -2 times 5, plus -5 times -2, positive 10. Row 2, second column, row 2, first column, -3 times -8, positive 24, plus -8 times 3, -24. Row 2, column 2, -3 times 5, -15, plus -8 times -2, positive 16. Oh, so what is that matrix? 1, 0, 0, 1. When I multiply a matrix times its inverse, I get this identity matrix. I'll show you in a little bit how to find the inverse. Right now I'm just telling you that that was the inverse. So I can verify that a matrix and its inverse are actually the inverses of each other by multiplying. Is there a way to make its inverse? Yes, but it's a little more complicated, but we will do that in a few minutes. If you're really sharp, yeah, but not always, because there's often a fraction multiplied through that's hard to see. I'll show you. Yes, sir. The identity matrix that we did before was the additive identity matrix. This one is the multiplicative identity matrix. The additive property, like, okay, for the property of addition, if the identity in addition is 0, because any number plus 0 gives me myself back. So 4 plus 0 is 0. 12 plus 0 is 0. Okay. For multiplication, the identity is 1. Because if I multiply any number times 1, I get that number back. 12 times 1 is 12. 3 times 1 is 3. So I have an identity for addition and for multiplication. So they're different. Just like in regular arithmetic, the identities are different for addition and multiplication. They're different in matrices too. Okay. Do you want to change your color scheme? No. Geez, why would I? Okay, so any matrix times its inverse is the identity. And it doesn't matter which way you write it, which way you multiply it. Which is not true when you're just multiplying any two random matrices. It's not always the same backwards and forwards. There's no commutative property, but there is for inverses. Okay, so we're going to figure out how to find the inverse, and we have to find something first. And the first thing we need to find is called the determinant. And we're just going to do a 2 by 2 matrix, because when they get any bigger than that, it just gets way too complicated. It certainly is, but it's